We'll show you how to predict whether a precipitate will form when two solutions with given concentrations and volumes are mixed. We'll do this by going through an example. We're given that 500 milliliters of 2 times 10 to the negative third molar PbNO3 is added to 300 milliliters of 0.11 molar KBr, and we're asked to use calculations to determine whether a precipitate will form. Beakers with these two solutions and the ions they contain are shown here. The left beaker contains 500 milliliters of 2 times 10 to the negative third molar PbNO3, and the right beaker contains 300 milliliters of 0.11 molar KBr. The lead 2 nitrate solution is poured into a larger beaker, like this, and the KBr solution is poured on top of it, like this. Then they are mixed. The final mixture contains all 4 ions, Pb2+, NO3-, K+, and Br-. And the final volume of the mixture is 500 milliliters plus 300 milliliters, which is a total of 800 milliliters. Possible combinations of ions in the products could be Pb2+ and Br-, which could form PbBr2, or K+ and NO3-, which could form KNO3. K+ and NO3- are both spectator ions, so KNO3 will not be a precipitate. Therefore, we can discard these ions from our diagram. According to the solubility table, lead-2 bromide is classified as having low solubility, so it could form a precipitate if the concentrations of the lead-2 and bromide ions are high enough. In order to find out whether a Pb2+ and Br- form a precipitate or not, we need to determine what is called a trial KSP for PbBr2. The trial KSP is sometimes called K-trial, experimental ion product, or simply ion product. Here we'll call it the trial KSP. The trial KSP of PbBr2 is calculated by finding the concentrations of Pb2+ and Br- in the new mixture, and inserting these into the KSP expression for PbBr2. It is called trial because these concentrations are not at equilibrium. Here's how it works. If the trial KSP is smaller than the actual KSP for PbBr2, then no precipitate will form. But if the trial KSP is greater than the actual KSP, then a precipitate will form. In order to calculate the trial KSP, we need to find the concentrations of Pb2+ and Br- in the new mixture. The source of Pb2+ ions was the 500 milliliters of 2 times 10 to the negative third molar PbNO3. When it was mixed with the other solution, the PbNO3 solution was diluted from 500 milliliters to 800 milliliters. Because PbNO3 contains 1 Pb2+ ion, the initial concentration of Pb2+ before mixing, which we'll call C1, is the same as the initial concentration of PbNO3 before mixing, which is 2 times 10 to the negative third molar, which we'll make a note of up here. In order to calculate the concentration of Pb2+ in the mixture, we used the dilution formula. C1V1 is equal to C2V2, where C1 and V1 are initial concentration and volume, and C2 and V2 are the final concentration and volume. Solving for the final concentration, C2, we get C2 equals C1 times V1 over V2. The ratio V1 over V2 is called the dilution factor. The dilution factor is always the initial volume, V1, over the final volume or total volume, V2. So to find the final concentration, C2, of an ion after mixing two solutions, we take the initial concentration, C1, and multiply it by the dilution factor, V1 over V2, or the initial volume over the final or total volume. So the concentration of Pb2+ in the new mixture, which we'll call the concentration of Pb2+ final, is the concentration of Pb2+ in the original PbNO3 solution, or concentration of Pb2+ initial, times V1, or initial volume, over V2, or final, or total volume. The initial concentration of Pb2 plus in the original PbNO3 solution was 2 times 10 to the negative third molar. The initial volume of the PbNO3 solution was 500 milliliters. And the final, or total volume of the new mixture is 800 milliliters. The milliliters will cancel out. We take 2 times 10 to the negative 3 molar and multiply it by 500 over 800, and the answer is the concentration of Pb2 plus in the new mixture is 0.00125 molar. And we'll make a note of that up here. Now we'll calculate the concentration of bromide in the new solution, or the concentration Br minus final. Since KBr contains one Br minus ion, the concentration of the bromide ion, Br minus, is the same as the concentration of the original 0.11 molar potassium bromide solution. We multiply the initial concentration by the dilution factor, which is the initial volume V1 over the final volume of the new solution V2. The concentration of Br minus in the original KBr solution, or concentration Br minus initial, is 0.11 molar. The initial volume of the original KBr solution V1 was 300 milliliters, and the final volume V2 is the total volume of the new mixture, 800 milliliters. Again, the milliliters can be cancelled out, and 0.11 times 300 over 800 is equal to 0.04125 molar. We'll leave this unrounded until the end of the calculations. And we'll make a note up here that 0.04125 molar is the concentration of Br minus in the new mixture. In order to determine the trial KSP, we start by writing the solubility equilibrium equation for lead-2 bromide, PbBr2. We use this to write the KSP expression for PbBr2 here. Because we're using concentrations of Pb2 plus and Br minus, which are added to a new mixture, but are not at equilibrium, we call this a trial KSP. We substitute 0.00125 for the concentration of Pb2 plus in the trial KSP expression. And we substitute 0.04125 for the concentration of Br minus in the trial KSP expression here, remembering that the concentration of Br minus is squared in this expression. So to calculate the trial KSP, we take 0.00125 and multiply it by 0.04125 squared, and we get 2.1 times 10 to the negative sixth for the value of trial KSP. Looking on the KSP table, we see that the actual KSP of lead-2 bromide, PbBr2, is 6.6 times 10 to the negative sixth. Comparing the trial KSP, 2.1 times 10 to the negative sixth, with the actual KSP, which is 6.6 times 10 to the negative sixth, we see that the trial KSP is less than the actual KSP. So when the two original solutions are mixed, a precipitate will not form in this case.